How we doing? Good. Ready to get back at it? He doesn't know. All right. Let's chat just briefly about syllabus type things here, and then we will get into it. Many of you already know me. If you don't know me, I'm Dr. Joe. Clean up the syllabus here. Sorry about that. I try to remember, I usually do, to record lectures in case you have to miss for whatever reason, or something wasn't clear, you want to go back and watch it, those kinds of things. So try to record it. So I'll write on the tablet. We'll do some things on the computer. Not a whole lot, but we'll use Excel a little bit when we talk about approximating solutions. We will use Python a little bit as well, here and there. So not much. Might expect you to do something on Excel on an exam. I would not expect you to do it with Python on an exam. That'll depend on how much time we have to get into approximation things, but I wouldn't expect you to do something with Python on an exam. So, in case you haven't dealt with it much, Python's actually pretty easy to get into if you have dealt with it, especially for the stuff that we're going to do, because we would use more built-in things and not have to do a whole lot of programming from scratch. We would just use the built-in commands that are there. So, like I said, we won't do a lot with it in here. If you have me the next class at 11, we'll do a lot more with Python in there. So, anyway, I'm Dr. Joe. My office is downstairs in the math suite. Like I said, many of you already know this. End of the hall. Good place to hang out and do homework if you got questions, for example. My office hours are there, but I'm here more than that too, so just give me a holler. My classes this semester are only Tuesdays and Thursdays, so if you need to see me on a Monday or a Friday, let me know that you actually really need me to be in person, or we could do something for email or for Teams or something along those lines. We can do something virtually as well. The book, the link should be active in Moodle. Should be set up right. If you have any issues, let me know, because I need to know that. The hard copy looks like this. You can probably get away with an older edition. I don't know if you're opting in or not to Big Blue Access, but you could probably get away with using an older edition. If you've got an older edition, the reason why I'm saying that is because they're cheaper. Okay. If you've got an older edition, just let's look at the homeworks and make sure they match up. I'm not going to collect homework, mainly because it's easy to let ChatGPT or Claude or something do the solution for you. So what I'm going to do instead is we'll have frequent quizzes, which is where you can see that down there in the grading part. We'll have frequent quizzes that'll be literally homework problems. So it'll be your advantage to work on homework problems. Okay. So we'll do that instead. I'm not looking for them to take a whole heck of a lot of time. They'll be at the end of the hours. Probably do that every Thursday. Not this coming Thursday. I'm not even going to give you a homework assignment today. All right, we're just going to chat about some things that are differential equations related, get an introduction into the material, and then we'll actually start talking about methods for solving such things. To give you a little bit of a hint about what you might want to use to solve differential equations, differential means derivative, so we're going to have equations that involve derivatives. So if you need to find a solution, what do you think you might need to do if you are given a derivative and need a solution? Or what do you think? What calculus operation do you think you need to do? You're given a derivative and you need to find a function. Well, this is not starting off well. Integral, yeah. So we're going to see a lot of integrals. So if you are looking for something to review this week, go review your techniques of integration. Okay. In particular, go back and look at U substitution. That's a big one. Go back and look at integration by parts. That's a big one. Okay. If you've got time, look at partial fractions. Those won't come up as much in the integrals to start with, but they will come up when we do a technique of solving differential equations later. Okay. So right away, make sure you can do U substitution integration by parts. Okay. Partial fractions will come up later. We will do a little bit of a review of partial fractions when we get to it. Okay. But coming hard and heavy on Thursday, we will do integrals. Okay, so make sure that you are familiar with how to do integrals because that will pop back up. All right. So anyway, just wanted to mention that if you're looking for something to do between now and Thursday, review your integration techniques, and in particular, U substitution and parts. Those will be the ones that'll pop up most to start with. Okay. You also do trig substitution in Calc 2. We will not be doing a lot with it, if trig substitution at all, and it would not be something that I would expect to do as a technique that would be on an exam. Okay. I might assign a homework problem. It might pop up in a homework problem. If it does, you can deal or let something else do the integral for you. I'm not going to expect you to do it on anything that I'm going to grade. Okay. All right. Sound fair? Okay. All right. Cool. All right. So quizzes, like I said, they will be directly out of homework. I'm not going to give you any homework assignment today because your homework assignment literally is go back and make sure you know how to integrate. Okay. That's the big thing. Well, we'll have 2 exams. More about exams when we get there and what they'll cover. We'll have 2 exams. There are a lot of techniques that we do in this class. And this class is about solving things, how you can do applications with where they pop up for solving things, which means that I'm going to give you either a sheet or open book or something along those lines for you to do the exam. Okay. The point isn't to try to memorize every single method that we're going to do, right? You need to be able to recognize what method to use and then be able to implement it. Those are kind of the 2 big things to do, all right? So you will have some sort of cheat sheet, something along those lines for the exam. So that doesn't mean don't study, by the way. That just means you will have you don't have to worry about trying to memorize what you need to do when you recognize this type of problem. And you'll see more about it as we talk, see what I mean by that more as we talk about these things. But it's literally pattern recognition. I see this type of problem when we apply this type of method. So the part that you're going to have to really concentrate on is how do I recognize what that is? And that's not really cheat sheetable, if you will. Okay? The method is how to recognize it. So, and then we'll have the final exam. I've got the final exam date listed, I think, in here because they already told us what it is. I know that's been a problem in the recent past with students don't know when the final exam is. So unfortunately, our final exam is at 8 a.m. I believe it's the Tuesday of that finals week. Okay. I don't set the final exam schedule. I wouldn't want to come in and take a final exam at 8 either. Okay. But that's when it's scheduled. You can also see when I've scheduled the other 2 exams. I forgot to do not disturb the launch here. First exam will be a month from yesterday, February 19th. And then the second exam will be on April 2nd. Remember that we don't have class on advising day, which is April 7th, which is why I've got that here. We don't have class on the 7th of April. So, standard grading scale, 90, 80, 70, 60. I reserve the right to lower the cutoffs, but not raise them. And so what I mean by that is, if you earn a 90% in this class, it'll be an A. There's no way that at the end of the semester, a 92 suddenly becomes a B. Okay? But it may be the case that maybe an 88 is an A rather than a 90. That's what I mean by that. I do plus minuses at the end. So if you have a 78, that's a C, right? Not necessarily a C plus, depends on things. I only apply plus or minuses in borderline situations. Typically, I use them as a bump up. That's not typical. I always use them as a bump up. It's always a round up thing for me. I don't knock anybody down. So if you're at the 78 range and you've been to class, it's not going to be hard for me to tell who's been in class and who hasn't. There's 7 of you. Okay? Not going to be really hard. Participate, do all those things, come to my office hours. I'd be inclined to give it a B minus. So it's always a bump up. I hated minuses as a student, so I try to make it a positive thing. So if you see a minus from me, it's because that's rounding up. As far as studying goes, this is a 300 level math class. You should expect to study, shockingly enough. Okay. Usually it's like 3 hours a class for every hour in. It's a 3 credit hour class. You should expect to spend 9 hours. It's a rough estimate, right? This material is not terribly theoretical. This is a nice thing, right? This is more of a computational type of class. So Once you get your techniques down, maybe you don't need to spend as much time on it at that point. Okay. Don't wait until the night before an exam to try to get your techniques down. But once you get your techniques down, it really is going to be about, I recognize this type of problem. I'm going to implement this type of solution for it. But come find me if you've got questions. Happy to answer questions always. So, no worries there. Email me if you've got questions as well. If I'm not around, if I will check my email up until like 10 o'clock at night. So you can always email me later. I'll answer. I don't have very good boundary setting as far as email goes. So if you email me and I see it, I will email you right back. So I'm trying to work on it, but I'm almost 55. Probably not going to figure it out at this point. Okay, so any questions at all about how we're going to run things? I will also encourage you, if something is not working for you in the way that the class is being administered, tell me, okay? I may not agree with you and let you know why I'm doing something a certain way, but if something is not working, don't wait until course evaluations to tell me something didn't work. That doesn't help anybody, right? I'm not going to be offended if you tell me that something's not working for you. We'll try to work to make it work for you, okay? I know it's hard. I know it's scary to try to do those things, to try to be confrontational, because you think it's a confrontation, and it's not. If something literally isn't working for you for whatever I'm doing, then I need to know. Well, again, I may not be able to change it. It may be like, no, this is why I'm doing it, and here's what we need to do. Let me help you get through it. That might be the conversation. But trust me, you're not going to offend me to say something like, this is sucking. I need something to help me, okay? Please come tell me, all right? And I know it's a scary thing to do. As long as you're not mean about it, that's okay. Okay? Don't be a jerk, and we'll get have a conversation, all right? There may be something that I can do to make it a little bit better. Maybe that's providing more resources. Maybe I record a couple of extra videos with extra example problems, right? Maybe there's just something that I can help you do, okay, to make it go better. So just let me know, and I will do my best to try to fix it. All right, cool. Any questions at all? All right. Well, let's see if we can get started then. Some of the stuff that we're going to do quickly, not because it's not important, but it's just that, again, the point of this class is to get to the point where we can solve differential equations, right? You're in this class for a reason. Differential equations is one of the most applied classes that you can get. They basically, you're trying to look at a situation, describe what's going on in the situation, how things are changing. I mean, if it's something that's not changing, there's not a lot of reason to analyze it, right? So something must be going on with the situation that things are changing. So you're trying to figure out interactions between variables and how those variables are saying what's going on with the change, right? So give you a quick example. Since it's cold and flu season, maybe you're looking for the rate that people are getting infected with the flu, okay? Well, that's going to depend on people who have the flu and their interactions with people who don't have the flu, right? So there's going to be a rate of change of how the flu is spread based on who has it, who doesn't, and what their interactions are, right? Then you'll also have, okay, well, once you have the flu, you get better, right? So you're also going to have a change not only for who's getting the flu, but who's also recovering from the flu, right? So you're going to have people who are susceptible to the flu, haven't had it yet, don't have any immunity to it yet. You'll have people who are infected with the flu. You'll have people who are recovered from the flu. That's what's known as the SIR model, by the way, of infectious diseases. It's a big model. And you describe it with a system of differential equations. We'll talk about systems of differential equations later. It's the point of this class, right? You're probably in a field that's going to require some sort of knowledge about how things are changing and try to solve those things. Be that physics, be that engineering, be that some biological applications, be that economics. There are a lot of different applications, be that chemistry, okay? A lot of actual physical modeling that you can do with different equations. Okay? On the flip side of that, what we do in this class is slightly disingenuous. What I mean by that is many of the differential equations that you come up with the model, you can't solve like. So that's another reason why we'll talk about approximation techniques. That'll come up later. This is also a good point to jump off from, that if you're going to do more and more applications later, you also do partial derivatives, right? You've seen them in Calc 2 or Calc 3. There's also a whole field of partial differential equations, which is huge in being able to describe things like, stresses on things and all those different ideas. And that pops up later. And almost every technique there is to do with solving partial differential equations is an approximation technique. So that's why we'll talk about it a little bit. It's a good jumping off point for studying things later. All right, enough of me yakking about things that don't really matter too much, and let's get into actually solving some things here. All right, so I've already alluded to this before. So all we mean by a differential equation, so just some definitions. Ooh, that's in red. I don't want red. All we mean by a differential equation is just, it's an equation, of course. Oh, my handwriting sucks, so if you can't read it, just tell me. I'll fix it. Okay. It's an equation involving a function I'll call it y of x, just to emphasize that my function y is the dependent variable, if you will, depends on the variable x, which is an independent variable, all right, involving a function and one or more of its derivatives. Oops. Pretty simplistic statement, right? A differential equation is an equation that involves derivatives. Literally what it says, okay? We are going to do this where we've got one, to start with, we'll have one dependent variable, one independent variable. We will bump this up later to where we might have multiple dependent variables, but still only one independent variable. Okay? So all of your functions will be in terms of x, or sometimes we'll make them in terms of t. Because again, when I said this, a lot of this is describing changes in physical models, if you will. Those usually change over time, so we use t. Okay, so, but again, we might have multiple dependent variables, but we'll only ever have one independent variable. Okay, and that's what makes this an ordinary differential equation. Okay, partial differential equations require multiple independent variables so that you take partial derivatives of them. Okay. So when you see the word ordinary differential equation, we're talking about a differential equation that has just one independent variable in it. Okay. Later on, we'll talk about systems of differential equations, but again, they will be ordinary differential equations. Okay. PDEs, partial differential equations, is another course. Okay. If you're interested in PDEs and want to do an investigation into them later, we're happy to do an independent study type of thing with that. Happy to do that. All right, anyway, so I didn't put the word ordinary in here. This is the definition of an ordinary differential equation. Whenever we say differential equation in this class, we will mean ordinary differential equation. Okay? All right. A couple more definitions here. The order of a differential equation. I don't want to write differential equation all the time, so I'm going to abbreviate it with DE. Okay. And we'll hardly ever say differential equations. We usually say diffie-q anyway. So DE, I'll say differential equation every time I write it. But I'm going to write it as DE just because I'm lazy. Mathematicians are inherently lazy. It's why we have symbols for everything. Okay. All right. order of a differential equation is the highest order derivative in the differential equation. One of the simplest differential equations that you come up with would be something that looks like this. Derivative of y with respect to x equals y. We'll solve that here in a second because it's not hard. The order of this differential equation is what? What's the highest order derivative we see? 1. Yeah, right? This is first derivative, correct? So it's a first order differential equation. Okay. We will concentrate on first order differential equations for a while, and then we'll switch to higher order differential equations and talk about different techniques of solving those. Okay. This is a first order differential equation because it involves the first derivative. Okay. If you were to write, if I changed this to it that way, make it a negative sign in front of it. What order does that have? 2. Yeah, it involves the second derivative. Okay. The reason why I wrote both of these is we should be able to solve these pretty quickly with what we already know. Okay. All right, let's look at the first one, and let's think about what the equation literally says. I take the derivative of the function, I get the function back. What function am I talking about? What function is its own derivative? Yeah, exponential function, right? It's e to the x, isn't it? Now, is it just simply e to the x? Or will some other one work? Could I put something in front of it, for example? Yeah, any constant, right? If I take 2e to the x, derivative of 2 to the x is 2e to the x, right? So in this first one, your general, and we call this a general solution, by the way. In this first one, we recognize that any constant times e to the x works, okay? And again, we call this a general solution. Oops, not a generate solution, general solution. Notice, though, and this is important to notice because we're going to come back to this idea when we're solving these things. Notice, though, every one of these solutions in my general case depend explicitly on that one solution, e to the x, right? If you've had linear algebra, you'll know this term. If you are taking linear algebra this term, you're going to hear this term. We have one linearly independent solution. Every solution in this equation can be written in terms of one thing. It's a constant multiple. Okay? So it has one linearly independent solution. Okay? I will use that term some as we go along. All you really need to know about linearly independent or dependent is that we're talking about linear combinations of things. And we'll talk about what that means in a little bit. Okay? Not a particularly difficult concept for what we need for. Okay? All right. Let's look at the next one. This one says I take the second derivative of a function, I get its negative. Can you think of a function or functions that when you take their derivatives, you get the same thing back, but it's the opposite? What do you get? Yeah, sine works and cosine works, right? Are sine and cosine multiples of each other? Can I take sine times a number and get cosine? No. So that's two linearly independent solutions here, right? When we get the general solution in this case, the general solution for this one is going to look like C1 sine x plus C2 cosine x. I can take any constant times sine function. When I differentiate it twice, I will get its negative. Right? The constant's not going to matter because when you take derivatives of a constant times a function, the constant just goes along for the ride. Right? So certainly that first one satisfies it. The second one also satisfies it. And if I add them together, well, we know derivatives break up over sums. So I can factor the negative out, right? So this gives me the general solution for that particular differential equation. I just said beforehand, is sine a constant multiple of cosine? You told me no. So now I have two linearly independent solutions for this differential equation, and I can generate all solutions from those two. Okay? This is what we mean by a linear combination, right? Usually when we talk about linear independence or dependence or linear combination, we're talking about vectors. If you had me for linear algebra, I said that a vector could be anything. In this case, we're treating our vectors as functions. Okay? This is a linear combination of the two functions. All we mean by linear combination is constant times the first thing plus constant times the second thing, and if there's more of them, constant times the third thing, constant. That's all we mean by linear combination. Okay. All right. Let's go back to the definition that we talked about, because this seemingly was lost in everything else I've been talking about because I like to babble. Right? What was the order of the first equation? 1. How many linearly independent solutions do we get? 1. What's the order of the second equation? 2. How many linearly independent solutions do we get? 2. That's not an accident, shockingly enough. Okay? All right. And we'll come back to that idea later. All right? But the order, especially in this special setup that we have, the order of the differential equation will tell you how many linearly independent solutions you have. This is a special case of differential equation. Okay, it doesn't work for every differential equation. It works for this particular type of class of ones. Okay. So far, so good. Not too bad. All right. Let's talk about a couple more definitions. A differential equation is a linear if. All right, well, let's think about what we mean by linear, and then we'll come back to this definition. Okay. Kind of just stopped, right? But let's think about what we mean by the word linear from algebra class and see if we can extend that to what we mean for linear for differential equation. Okay? All right. So, pardon me. When you think about a line or a linear equation or a linear function from algebra, what's the general equation of a line? Y equals mx plus b works just fine, right? We got y. Any powers on the y? No. Is y inside of a function? No. None of that stuff, right? Y is y, right? Did some stuff with the x, right? But the y is a y, right? No y squared, no 1 over y, no sine of y. Y is y, right? That's exactly what we need for a linear differential equation. Not worried about the independent variable. We're worried about the dependent variable and what is being done in the dependent variable. Okay? So when we say a differential equation is linear, what we mean is that if we have the differential equation, I'm going to write it a little bit funky. If we can write the equation in the form so I'm going to take my nth derivative, so this differential equation is going to have order n. If I use an n, assume that I mean that it's going to be a non-negative integer. Okay? So I'm not going to try to trick you with doing somehow do an inverse derivative kind of thing. I mean, that would be integration, but I'm not going to try to write anything goofy that way, right? So say I solve this for the highest order different derivative that we see. Okay? So then this will be, say I'll write it as f1 of x times the n minus first derivative. It's a minus 1. And then another function times the n minus second derivative. And keep doing this Oh, I really should have not done that way. That's okay. I should have made my subscripts on my F's match my order of each of the derivatives that I'm taking, but I've got them flip-flopped. I'm not going to rewrite it at this point. Okay. Whew, that's a lot of writing. This is what we mean by a linear differential equation. Okay. Let me give you a second to write the rest of it down. Don't worry so much about the notation, because it's not as hard as it looks. That looks ugly from the notation. 100% agree. Okay? That looks like garbage. Okay. Well, let's talk about it. And in particular, compare the form of what I have written for that equation to the second general solution that we wrote down to the second differential equation we solved. What makes it linear? Well, up here, I did stuff to the x's. I said I don't care about what we're doing to the x's. The x is the independent variable. I care about the dependent variable, right? If I look up here, my y is all by itself, right? Okay. That's why we call it a linear combination, right? It's a linear combination of those two functions. We have to bump it up a little bit because not only do we have a y involved in our differential equation, we also have derivatives, correct? But when you see the derivatives in what I've written, do you see those derivatives as the inside of any function? Are those derivatives inside any function? No. They're all standalone, right? Did I multiply any two of them together? No, they're all standing alone, right? Right? If you've had linear algebra, if you've had anything that talked about solving systems of equations, so not even linear algebra, college algebra, okay? When I have a system of equations, usually you'll write y equals, say, ax1 plus bx2. And then y equals, or usually have an equation, but whatever, maybe you have a number. ax1 plus bx2 equals c1, whatever, doesn't matter, right? But you've got two variables, they're not interacting at all, and they're not inside any function. That's what makes a linear equation, generally speaking, right? Same idea here. This looks ugly as all get out, I agree. But what makes it linear? That y, not inside anything. That derivative, not inside anything. That derivative, not inside anything, and all the way up the line. Okay? Also, you gotta be careful, you can't multiply them together. So it's not enough to just say they're inside of a function. I can't take y times y prime. That doesn't work either. It's non-linear. Okay? So linear is a very special case. They really are standalone terms when you write them. Does that make sense? Don't care about the f of x's. Okay? Those are okay. Those can be non-linear to your heart's content, right? This could be a sine of x here. This could be a log of x here. This could be a cube root of x here. That's all okay. Right? That's not what makes an equation linear. It's just the dependent variable piece. Make sense? Okay, cool. All right. Just want to make sure we have the definitions down as we're going along. All right, cool. What do we care about with these differential equations? Well, again, we're talking about trying to use differential equations to model physical phenomena. Okay. Bad news is that we got to get through some stuff. We're going to try to motivate things through models, but we won't have a lot of time for modeling. Okay. Leave that for other classes that you'll take that require the modeling. We'll just concentrate more on the solving. Okay. I will throw some modeling in there here and there, but we're going to concentrate more on the solving than the modeling pieces. Okay. I know it sucks because so many people are here because they're doing science and you want to talk about, well, how does this apply? I promise you can apply the crap out of this class, okay? It's just the only one semester, that's all we got, right? If we had 2 semesters, we could do more modeling, right? If you're really interested and want to do an independent study, we could do modeling out the wazoo. So, all right. Let's talk about what we mean, though, when we want to solve some things. All right, so let's look at some of the problems here that are in your text. This is number 14 after, well, like I said, if you've got an older edition, This is number 14 out of, in my edition, it's section 1.1. That's a little funky. Looks like 2 overlapped S's. That's just a funky notation for section. I'm old. That's what it looked like in old books. Okay. All right. 1.4, section 1.1. Oops. We've got dy dt plus 20y equals 24. All right. It wants us to verify that y equals 6/5 minus 6/5 e to the negative 20t is a solution. Before we do this, because the actual doing this is not difficult, let's talk about this for just a second. We have this written as an explicit solution. What I mean by explicit is that I have y equals function with no y's in it, right? That's an explicit solution. That's kind of, I don't even know what word I want to use. I'll say holy grail of what you want, right? If I can get literally what y equals, that's great. A lot of times, though, you may not be able to solve for y exactly. Okay? I might not be able to get y by itself. If you have an equation that involves x's and y's, or in this case, t's and y's, but I can't solve for y in terms of t explicitly, we call that an implicit solution. Remember you talk about implicit differentiation back in Calc 1? Same idea, right? I don't have y solved in terms of x to differentiate explicitly. Same idea here. I don't have an explicit solution. This is an explicit solution. This solution, actually, to this one is really, really nice. What I mean by that is sometimes when you find a solution, you have to worry about the interval in which the solution actually works. Okay? In this case, I don't have to worry about that because of the way the function, the equation is set up. We'll talk about that more as we go along. All right? They talk about it in section 1. We will definitely concentrate on when your solution is valid. Mainly, you have to worry about things like, do I jump across a discontinuity? Okay. We will get more into that. I'm not worried about that right this second. Okay. You'll see that in the text it says, find a solution or find an interval for which your solution is valid. I'm not as worried about that right this second. We will worry about that more later when we start getting more in depth into things. Okay. All right. I want to verify that it's a solution. Well, this sounds like stuff that you've already done before in your life. If I give you an equation, for example, if I give you the equation qx plus 5 equals 11, how would I check that 3 is a solution? If I say I have the equation 2x plus 5 equals 11, I say verify 3 is a solution, what do? You plug it in and see if it works, right? 2 times 3 plus 5 equals 11. What do you think you want to do in this case when I want to verify this is a solution? Plug it in and see if it works, right? A little bit more work because what do I have to do to plug it in on that first term on the left-hand side? What do I have to do to the function first? Take a derivative, right? But that literally is all you need to do. To verify it's a solution, you plug it in and see that it works, right? This says if I take the derivative of my function and then add 20 times the function, I better get 24. What it says, right? Okay, well, let's do it. What is dy dt in this case? It's 24e to the 20t, right? Or negative 20t. Right? Derivative of e to a power is e to the power. Derivative of the power is negative 20 in this case, right? Negative 20 times negative 6/5 gives me positive 24. It's been a while since I've done derivatives too, so I want to make sure I check my answer. Okay? All right. So if we do dy dt plus 20y, you just said dy dt was 24e to the negative 20t plus 20 times the function. Well, I'm betting 20 times 6/5 is 24, since we just did that a second ago, right? So we've got 24 e to the negative 20t plus 24 minus 24 e to the negative 20t, which really does equal 24, so it checks out. That's it. Literally, that's all you have to do to verify it's a solution. I literally plug the answer that they give you into the equation and show that it works. You've done that ever since you started learning algebra to work, right? Questions on that at all? I said I was going to mention more about when solutions are valid. I just want to look at a particular example, and you tell me when you think it might be valid. And like I said, we will go into more detail with this later. I want to see where your intuition's at. All right? Let's look at number 16. They give you the equation y double prime plus y prime equals tangent of x. And I'm not going to worry about the form of the solution they give you. So look at that equation. First, review definitions. Order of that equation is second order. 2, right? Second derivative. Cool. Pardon me, is it linear or not? Yeah, because we're just looking at, remember, we're looking at don't care about the x, right? Don't worry about tangent of x, it doesn't matter. Okay? We gotta get the y and the y double prime. Are they inside any functions? No. Okay? Are they multiplied together? No. So we're good. Right? This is a second order linear differential equation. We're going to come back to, these are actually kind of cool to solve because they just go back to algebra classes. We'll talk about this probably next week. They have constant coefficients. This is a really nice differential equation to solve. At least I think it's a really nice differential equation to solve. Okay. This part over here, since I'm just going through another definition that we'll talk more about later. That part over there is not 0. It's tangent of x, right? That makes it a non-homogeneous differential equation. Okay. If it were equal to 0, it's homogeneous. Not equal to 0, not homogeneous. Okay. Going back to linear algebra, we talk about homogeneous systems where you had a 0 on the right-hand side. Non-homogeneous systems don't have zeros on the right-hand side. Same word, same meaning. Okay. Again, if you haven't done linear algebra, it's fine. We'll talk about that linear algebra when we need to solve our stuff. Okay, just trying to connect it to classes that I know some of you have had. Anyway, part of the directions of this particular problem and the previous one, but the previous one was nice, right? Well, look at the previous problem. I don't have any x's in my original functions, right? Or in my original equation, right? I don't have any issues with that first one. That's a nice solution no matter what. Okay? Looking at my second one, again, my y's aren't bad. But what about this guy? What about that function? Any issues with tangent? Yeah, it's not continuous at odd multiples of pi over 2, right? It's sine or cosine. Cosine has zeros, correct? So if you're looking for a solution to this particular differential equation, do you think you would have a single solution, say, in the interval from 0 to pi? You think one, say it a different way. Do you think you could come up with multiple solutions that weren't constant multiples of each other necessarily? If I were allowed to go from 0 to pi. What I mean by that, let me draw a quick picture. I know my tangent function looks like, if this isn't a graph of the solution, by the way, this is just a graph of the tangent, the right-hand side. Okay? But it'll illustrate, I think, what I want, what I mean. All right, here's 0, here's pi over 2, here's pi. So going back to, I know it's a little hard because we haven't done a lot of it. We're going to do a whole lot of theory. We only need a little bit of theory to understand what we mean by the solution. Going back to the first two examples I gave you, I said that we found the general solution by taking, for the first one was just constant times e to the x. For the second one is a constant times sine plus a constant times cosine. And I said that I can write every single solution like that, right? Okay. But notice that my equations didn't have any bad spots, right? I didn't have any discontinuities, okay? Notice here I've got a discontinuity. So, in particular, I could, this is not the solution, okay? Or a solution at all. I'm just talking about this particular function. But notice that if I look at this right-hand side here, okay, and just leave it by itself, I could take a constant times this one and flip it upside down, just do a negative times it, right? Notice this looks kind of the same. I just flipped one side, right? But is what I came up with, just this part that I circled, is that a constant multiple of what I originally started with? The original function is the one in black. I'm saying my new function is just this one in this part. Is that this part a constant multiple of the one in black? A single constant multiple of the one in black. I know I came up with this piece by flipping this one upside down. Can I use one constant on the whole thing and get this? What constant can I use? Yeah. Well, if I do negative, what does that mean to? I mean the whole thing, right? I know I can't, right? Because I've piecemealed it together. What that does with solutions is it can make you be able to piecemeal things together that are not constant multiples of each other. Let me give you an explicit example. Anyway, the whole point of this one was, can you find a solution where you would, find an interval that would give you unique pieces, right, for linear combinations? And yes, you can, but it has to be between like negative pi over 2 to pi over 2, or pi over 2 to 3 pi over 2. If you try to jump across discontinuities, bad things happen. It's not unique anymore in some sense. Okay. Let me give you an explicit example of what I mean by this. All right. This is actually an example in the book. Change this back over to black. This is example 10 in your book. Well, in my book. Okay. Example 10 has x times y prime minus 4y equals 0. Okay. We'll talk about methods for solving this, but maybe we can guess it. I need to take a derivative of a function. I'm going to multiply it. I'm going to take a function. When I differentiate it, I'm going to multiply it by an x. That's what the first term says, right? That needs to cancel with the original function. Don't worry about the constants. Just think about it for a minute. I need to take the derivative of the function. I'm going to multiply it by an x, and it's going to cancel the original function out. What kind of function do you think we're taking a derivative of if I take its derivative, I bump the power of x back up by 1 again, and it cancels the original? What kind of function do you think we're talking about? Is it sine? Is it a sine function idea? No, because I don't get an x that pops out, right? What kind of function are we taking a derivative of? The power, right? It's going to be a power of some sort, doesn't it? Right? Because I'm differentiating, I'm bumping the power back up by 1, and it's going to match the power on the other one, right? So it has to be some sort of polynomial, right? You agree? You think we can figure out an explicit polynomial that's going to work? Okay, when I bump the power back up by 1, I've got to make the constant match with a 4. Remember your power rule? But x to the n, what happens at the end? Goes down the front, right? So if I need to multiply the original function by a 4 to make it cancel, what do you think the original power was? 4, yeah. So this is probably x to the 4th, right? Does it work? Well, let's check. X times derivative of x to the 4th is 4x cubed, good. Minus 4 times x to the 4th. I really do get 0, right? Really do get the same thing. Okay. Is that my only solution? Would 2x to the 4th work? Two times x to the 4th? I think it does, doesn't it? Because I just get an 8 and an 8, right? If I did negative 3x to the 4th, I'd get a negative 12 and a positive 12, right? It would work, right? So any constant would work. Okay? Again, we would call this a general solution. All right. However, in this case, we've talked a little bit about uniqueness, right? In those first two examples, it got chilly in here. I heard it turn it off, didn't it? I was getting warm, and I was like, okay, turn it back on again. Sorry about that. Apparently, it's back cold outside. Anyway, we said that we had those two original differential equations that we started class with that we had the general solution. That was how we could write any solution, right? I claim that this is not the only way to write all the solutions that are possible. I think there's another one that's not a constant multiple of x to the 4th. Okay? Let's see why that is. And then talk a little bit why it happened. All right? Okay? So let's look at this function instead. What if I had y equals x to the 4th, where x is greater than or equal to 0, and negative x to the 4th when x is less than 0. So let's think about what we did to this function. X to the 4th kind of looks like x squared. It's just flatter in the middle, steeper on the sides. Right? When we multiply it by just the left-hand side by the negative x to the 4th, we just get this part gets flipped. This part is still like this, right? Kind of like x cubed, kind of like x to the 5th, but in between is the 4th power, right? All right. That second one that I drew is that a constant multiple, a single constant multiple of the original function, the x to the 4th. No, it's not, right? Because I flipped one side and not the other, correct? Right? So it's not a constant multiple, but does this one work? Does this function work? Well, if I'm greater than 0, I differentiate this function, which I already said works. If I'm less than 0, I differentiate this function, which we already said works. So this also is a solution, right? And a constant multiple, this one will work. Okay. So this one gives me a general solution, but it's not the general solution because I've got another one that's not a constant multiple of any of those. It's outside of that family. Okay. What happened? Well, I said discontinuities are bad things, right? When I wrote down that equation, and that long thing that I said that this is a definition that was ugly with all the derivatives and powers and all those things, I had solved for the highest order derivative, right? What happens if I solve for y prime here? What happens? What do I have to do with the x? If I want to solve for y prime, what do I have to do with the x? Not a trick question. If I want to solve, get y prime by itself, what do I have to do with the x? I have to divide, don't I? You got an X in the denominator. I made something discontinuous, didn't I? Yeah, that's what happened. Discontinuities cause bad things to happen. Okay? There is an entire field that's devoted to trying to solve what are referred to as boundary valued problems. We're going to talk about some boundary value problems in here. Boundaries get weird. When you get things that are discontinuous, things get weird. We're going to talk about this in numerical analysis if you're in a numerical analysis class. When you get close to discontinuities, bad things happen. It's hard to approximate, for example, right? I get those vertical asymptotes, it's really, really hard to approximate. Uniqueness goes away when I make a discontinuity. Okay? So what I mean by that is, if I'm to the right side of 0, that constant times x to the 4th is a unique solution depending on where you start to draw it. Okay? We refer to that as an initial condition. We'll talk about that here in a minute. Okay? On the right-hand side of 0, we have no uniqueness problems. On the left-hand side of 0, also no uniqueness problems. But if I try to include 0 in my interval, I get uniqueness problems. Okay? Because I can have this mixing and matching of the pieces, right? I could do any constant I wanted times the left-hand side, and I can do any constant that I wanted on the right-hand side and make a piecewise defined function, and it'll work. Right? It causes uniqueness issues. They're not all in terms of the same function. Does that make sense? Okay. So when the problem asks you, what is the largest interval where you can make a unique solution? In this case, it would be 0 to infinity or negative infinity to 0. Those two you can do. I can't include 0 anymore. Just the moral of the story, worry about discontinuities. Okay? Anyway, any questions on that at all? I know that was lots of words. All right. So that gives us a kind of an introduction to what's going on. Let's move on to, I might have missed a couple of things here and there. If there's something that I think you need to look at in particular, I will assign a homework problem to let you go investigate the reading. And of course, you can always ask me questions. Kind of the point. All right. Section 1.2. Initial value problem. So far, the differential equations that we've talked about, I haven't talked about a specific solution, right? I've talked about general solutions. Here's what a whole family of solutions have to look like. Typically, we call that a parameter for the solutions. So when we had y equals c e to the x, that was a one parameter family. When we had the y equals c1 sine x plus c2 cosine x, that was a 2 parameter family. Just counting the number of constants that we have is all we're talking about, not anything exciting. That's why I didn't talk about it then. All right. Anyway, so a lot of times though, you are given a specific scenario and you want a specific function to model that scenario. To give you one that you've probably done before, you say you have a colony of bacteria and there's 15 bacteria present at time 0, and then every 30 minutes the bacteria double. The number of bacteria doubles. Can you find a function that models that scenario? And that's all exponential growth, right? Or I have 500,000 atoms of uranium-235, and the half-life is this, and right? Those are all exponential growth or decay, right? You've had those ideas. When I tell you I had 15 bacteria present at time 0, or I initially had 500 grams of uranium-235 initially, those are initial conditions. That's what we mean by initial conditions. When you have an initial condition and you want to find the solution that satisfies that initial condition, that's what we refer to as an initial value problem. Okay? All right. So, when you have, we're going to write this in a little separate form here. So, let's say we want to solve Remember I talked about solving the equation for the highest order derivative? I'm going to write this a little bit differently. This, I think your book refers to this as the normal form of the differential equation. Basically, all we're saying is that we are isolating the highest derivative, the highest order derivative. The right-hand side is just in terms of x and y prime and y double prime and all the way up to the n minus first derivative. That's all that f of thing means, right? Before, when I wrote it down, I wrote a big long thing on the right-hand side. This is just shorthand notation for something that looks like that. The thing that I wrote on earlier, that was for a linear differential equation. This may be non-linear. This is normal form. When we want to solve this subject to the following. This is where the initial conditions come up. Okay, so we need to know something about what happens to the original function at a point. We need to know what happens about the derivative at the same point, the second derivative at the same point, and that's n minus 1, yep. The n minus first derivative at that point. Those are all what are known as initial conditions. This is different than boundary conditions. These are initial conditions. Notice what the inside of each of those functions is all the way across. Did I change the x value? No. That's what makes it an initial condition. You are given the information of the function and its first n minus 1 derivatives at a single point. Okay? Boundary conditions would mean I would use multiple points, usually 2. Okay? This is initial condition, right? This is what makes an initial value problem. Okay? This is an initial value problem. Oops. Okay? Let's go back to what we talked about earlier. Let's go back to that example where I had the second derivative was equal to the negative of y, right? You already told me that the general solution was this, right? Okay. Let's say I also tell you that y of 0 is 1 and y prime of 0 is negative 2. I'm just making up numbers. Hopefully they don't be too gross. I'll use 0 in particular because that's like my equation solving easier. This now I've turned the original second order differential equation into a second order initial value problem. By the way, why did I need 2 initial value, 2 conditions here? How many constants do I need to solve for? 2, right? So trying to lead up to what we're going to be doing later, because again, this is just an introduction into definitions and so forth, right? We're going to do actual solving, like I said, on Thursday. We have 2 constants that I need to solve for, right? I need 2 things to tell me what those constants have to be. I need 2 equations to solve for the 2 unknowns, right? Now, I told you that the second order typically has 2 linearly independent solutions, which gives you the 2 constants. When I start with the original function and go down and take the derivatives up till n minus 1 of them, I get n equations. It'll give me n values to be able to solve for those n constants that I'll get. Okay? Right? 0th derivative, original function, if you will. First derivative gives me those 2 equations to match up with the second order differential equation. Now that I have this general solution, I just use this to set up a system of equations to solve for my constants. Okay? Here's my original function. I can differentiate. Be a little bit careful here. Not that you can't differentiate sine and cosine, but a lot of times you argue when you have an arbitrary constant that I can just absorb things into it, right? Usually if I take a constant and multiply it by a number, I just absorb it. It just stays an arbitrary constant, right? I don't want to do that here because I'm trying to figure out the exact solution here that works in this case. That means my C1 and C2 aren't arbitrary. They're fixed. I'm trying to figure out what they are, right? What I mean by that is when I took my derivative of my cosine and got a negative sign, I want to make sure I have that minus sign still here. I don't want to say, oh, it got absorbed by the arbitrary constant. It's not arbitrary here, okay? It really is a fixed constant. I just don't know what it is versus an arbitrary constant that you would have when you do a general antiderivative. Does that make sense? We're going to do that, play around with that some later, where you kind of absorb things in. You got to be careful when you do it. Is what the whole point of this is. All right. Anyway, now I can set up my system of equations. It's pretty easy, right? Using this first one. I know I shouldn't say easy. This is stuff you've done before, right? Easy, just in my mind, in my brain, is quick. Doesn't necessarily mean not hard. Okay. So if I say something that is easy and you don't understand why it's easy, ask. Because it means all I mean by easy is it's fast. Okay, once you figure out what's going on. Okay. What I mean by easy here is this is what I plug in for x. This is what I have to get out for y. All right. So using this first equation, what equation do I get for C1 and C2? What's going to go on the left-hand side? 1. That's what the y value has to be, right? What goes on the right-hand side? You don't have to actually simplify it yet. You can just tell me what's on the right-hand side. Yeah, C1 sine of 0, good. Plus C2 cosine of 0, right? That's all I mean by easy, right? It's quick. I just plug it in, right? Just got to plug in the y for the y and the x for the x. Okay? What's the second equation going to be? What goes on the left-hand side for the second equation? Negative 2, because that goes in for y prime. What goes on the right-hand side? Well, C1 cosine of 0 plus, minus C2 sine of 0, right? Now, I picked 0 because it makes it really, really easy, doesn't it? Sine of 0 is 0. Cosine of 0 is 1. So C2 is 1, right? Over here, C1 is negative 2. Oops, not that way. So you get negative 2 sine x plus cosine x. That's your solution to this initial value problem. We typically refer to this as a particular solution. At least I refer to it as a particular solution. Because it's the solution for this particular initial value problem, right? It fits the form of the general solution. It's just the solution that works for that set of initial values. If you change your initial values, you'll change the solution. Okay. How do I know that if you change the initial value, you'll change the solution? Well, looking at my original differential equation, do I have any continuity issues? No. So I know it's going to be whatever I find will be work anywhere, right? And that's basically the crux of what's going on. So they mentioned this briefly at the end of section 2. This is theorem 1.2.1. If your this is, I'm going to write something here that's weird. If this differential equation, when I write it in normal form, is nice, then the initial value problem, which we'll abbreviate IVP, initial value problem, has a unique solution in the nice region. I got to tell you what nice means. I'm not going to write it all down. Okay. They give you a little bit more of a definition of what they mean by nice region in the book. But the nice region in the book is just for a first order differential equation, and the more general version works for the nth order differential equation. What do I mean by nice? I've already alluded to it a little bit. When I have discontinuities are checked, right? Okay, so things that are not nice are discontinuities. Okay? What needs to be continuous? Oh, that's a loaded question. Remember your partial derivatives. Okay, this function has to be continuous, the way this is written. Okay, but I also need to worry about the partial of this function with respect to each of those things. In particular, with respect to y. But I have to worry about the partial derivatives being continuous as well, in particular with respect to y. But I need a region that has no discontinuities of the function as it's written plus partial derivatives of those pieces. Okay? Well, I didn't write it all out. We're not going to worry about it too much. Just know that when you get discontinuities, you limit where the solution is unique. Okay? That's the idea. Okay? We're definitely not going to do that here. Okay? Well, no one wants to do that, including me. I don't care. Okay? Again, the moral of the story is, if you get an initial value problem, okay, look where the discontinuities are, because you're only guaranteed a unique solution in between where discontinuities would be. Okay? And then, of course, more generally, if you've got a function with more variables, you get regions, right? But that's the idea. Okay? So if I look at, let's look at a specific example, and then we'll stop. Let's look at number 18. We've got y prime equals root xy. This is written in that normal form because I have it solved for y prime. Again, first order, right? Is this linear? Or for linear, you concentrate on the y piece, right? Is y inside of a function? Yes. So is it linear? No. Under a square root, right? Not linear. All right. So where is this thing going to have issues? Well, this is my function of xy, right? Agreed? Okay. Where is this going to have issues? Well, I've got a square root piece here, right? When does square root have issues? Negatives, right? So I better make sure that either both of my variables are positive or both of my variables are negative, right? So right now I'm either in quadrant 1 or quadrant 3 to get any type of solution, right? If I cross from quadrant 1 to 3, you think I'm going to get a unique solution? No, because I have 0 p's, right? Where does that come in? If I do the partial with respect to y, that's a y to the 1/2 power. What happens when I differentiate a 1/2 power? I get a 1/2 y to the negative 1/2. I'm going to get a continuity problem of 0, right? Okay. So if I'm looking for a unique solution to this particular problem, it's either going to be x is greater than 0 or x is less than 0, but not letting it cross. I got some other things to worry about as well, But it's that continuity piece that I have to worry about. When I start jumping across things. Like I said, we'll concentrate on that more as we write down solutions and look for particular solutions, those solutions to IVPs. Because again, I don't want to say my IVP works all the time if I jump across a discontinuity. Okay. And basically, that's what we're going to look for, the discontinuities. It'll end up boiling down to that. Does that make sense? All right. We'll do more of this next time. Oh, shoot, I'm a minute late. Sorry. We'll do more of this next time. Have a good one. We'll see you on Thursday. We'll talk slightly about modeling in section 1.3 on Thursday, and then we'll get into solving some things. Okay. Have a good one. We'll see you then.